Okay, I think we'll get started. Thank you so much for joining us. My name is Heather Galt. I'm going to be your host for today. So, Olga, if I can just get you to maybe go to the next slide. Before we jump into the webinar, a couple of little logistical things for us to cover off. So, first of all, if you do have questions during the webinar, I would just suggest that you add a question and answer in the Q&A button, which is down at the bottom of your screen. So you'll see a Q&A button, excuse me, right at the bottom beside raise your hand, chat, and so on. So if you just click on that Q&A button, you can add a question. I will see those questions and we'll either interject as the presentation's going on, or we'll wait until the end, just depending on what that question is and how the presentation's going. There is a chat function as well, which allows you to chat with both Ola and myself. So you're more than welcome to use that throughout the session, and I will be monitoring that as well. We are recording today's session, and that session will be available to all of you afterward, probably in about 24 hours through both PPO's YouTube channel and also through our website. And we'll be sharing a recording with everybody as well as part of our follow-up email. If you're interested at the end of this session, we do have a number of other webinars and other resources available on our website at ppo.ca/resources, or you can find us on YouTube at youtube.com/ppoptica. So please feel free to check those out as well. So I'd like to introduce you to our speaker for today. Olga, or Ola, as we affectionately like to call her, is our CEO. Ola's been with the company for many, many years and has over 25 years of experience in image processing and spectroscopy across many different industries, including oil and gas, aerospace, and of course, the meat industry. She's been working as PPO has with the meat industry for about 10 years now and has worked with a number of the major processors, both in North America and globally as well. Ola has her background in medical biophysics with a master's degree and an undergrad in engineering. And she's also a member of the Meat Institute board and a member of the Bioenterprise board here in Canada. So very deeply embedded in the industry across the board. And Ola, with that, I think I will turn it over to you to get us started.
Thanks, Heather. Wow, I sound impressive to myself. So today we will cover several topics, and thank you everyone for joining us. I know December is where we are is always a little bit gloomy, so hopefully I'll shine some light onto your questions about detection. So I will talk a little bit about detection approaches, whether it's using people, X-rays, metal detection, multispectral and hyperspectral, but I'll also talk a little bit about statistics and probabilities. I know that sounds scary, but to understand what it means to detect, it is to understand probabilities and statistics a little bit. So hopefully I won't overwhelm you, but hopefully it will give you a better idea of what it actually means to detect a foreign material, for example. I will also give you a few examples of our detection system, and then talk about how we talk to our customers on the plant floor, in operations, to engineers and FSQA members as well, because the problems that you're facing in your day-to-day are different than your colleagues, and hopefully we can kind of address problems that you might be seeing in your work. So let's jump into what is detection. And, I always laugh that, yes, a perfect system for detection of issues does exist. And essentially that system rejects everything. So if you think about medical diagnosis, essentially, if you're afraid of cavities, we should all pull out our teeth and therefore we'll never see cavities. And that is very ridiculous, but unfortunately it's true. There is no such thing as a perfect detection system. So we have to think about what it is that we're trying to solve. And in the space of, in the food and meat industry, in the space of all foreign materials that might be in your product, only some of them will be found with whatever technology you choose. And that's just how things go. But that means that you really need to understand what foreign materials are the biggest issue, and also how you could make things better in the plant, and which technologies to choose for which types of materials. So as I mentioned before, good understanding of your problem is very, very critical. picking the right approach, and then understanding trade-offs. Obviously, it would be fantastic if we could implement 20 technologies at every step of the way in your process, but that's just too expensive and not feasible. But as we're seeing with more and more of our customers, multi-hurdle approach or many methodologies of detection of foreign materials really work the best. And that's not necessarily detection. Some of it is prevention of foreign materials going down the process line. So, how do we talk about detection systems? Everybody always goes, well, I need to detect the smallest piece of whatever it is that I can find in my stream of product. And unfortunately, a minimum detectable object varies depending on the technology, but also on your product and how your system is configured. So really, what you're talking about is the probability of detecting a given object at a given size. And that's really only visible on something called the detection curve, which essentially shows you size of the object and probability of detection. So obviously, as very small objects are difficult to find, large objects are easy to find even with technologies that are not very suited for them. So, if you have a huge chunk of plastic embedded in a chicken, even X-rays will find those. So detection curves are very important. And again, we're talking about probability of finding something through your system. And this is another way of thinking about it is probability that there are no foreign materials in your stream of product, and what is the likelihood of foreign materials being present. And those distributions are very different, and I'm trying to show them in these plots. So for the most part, in a typical plant, we're seeing maybe 5 or so foreign materials in a week, and there are thousands and thousands of pounds of product going through. So obviously the likelihood of foreign material being present is extremely low comparing to likelihood of no foreign material being present. And so it's very important to think about detection systems. Not only do they have to find true positives or detect foreign material, but they also have to not over-reject. So they cannot reject good material. And that tuning or that threshold of detection is very critical. So in this plot, for example, I'm trying to show that you have a distribution of foreign material or likelihood of finding foreign material, and you tune your system to detect as many of these as possible, while still not over rejecting the clean materials. And this terminology of true positives, false positives, true negatives, and false negatives is very critical in being able to kind of understand what's going on with your system. So for example, what does it mean to be a true negative? Well, not only does your system not reject it, but there actually isn't a foreign material in it. But a false negative is there is a foreign material present, yet your system didn't reject it. False positive is we rejected something that was clean. And then true positive is what you actually want the most of, is only foreign materials were rejected. And this play between sensitivity of the system and specificity of the system is critical. So the system detection threshold is extremely important to determine. And that's something that a good detection company will work with you to figure out what your process can stand and what kind of needs your specific operations have. So for example, a very sensitive system will reject most of the foreign materials, but unfortunately will over-reject. A very low sensitivity system will not reject almost any of the material that you don't want to reject, so clean material, but it will miss foreign materials. So what trade-offs are you willing to make? Is it important to have all your good material go through, or are you willing to take some losses, or are you willing to re-inspect material that might be clean, but your detection system rejected? So again, those are discussions that a detection company like ours will have with you multiple times. And I'll talk a little bit about, for example, how to measure return on investment and what the costs associated are with setting that threshold of sensitivity of your system. And the other thing to really consider is, the smaller the object you want to find, for the most part, most detection systems have a difficulty finding this. So yes, we can, X-rays can find 0.8 millimeters, for example, of a stainless steel bead, but they will not be able to find 0.4 millimeters. Or something like that, right? So every detection system has a limit, and even humans. I'm always amazed at how good people are on for detection of small objects. But what's interesting is humans will miss some of the big objects going through because they can't pay attention all the time. So again, thinking about your foreign materials, what's present, how do they look, how are they presented, and what your process requires from you is very critical in picking the right detection system. So let's talk about different inspection options. I will talk a little bit about people and then go through different technologies available. And people are really, as I mentioned before, really, really good detectors for the first 10 to 30 minutes of being on task. We lose attention span very quickly. And yes, you can train human operators to pay more attention and whatnot, but let's face it, we have all seen this. We go to a plant, the moment, the supervisor hard hat is visible at a plant, everyone is looking and finding everything available. And somehow around lunchtime on a Friday, it doesn't matter how many people you put online, but they will not find a single foreign material. And that is human nature. And unfortunately, humans are affected by their environment. So it doesn't really matter what the object is that they're supposed to find, but, they will worry about noise and temperature and social pressure and how well they've been trained and how well they're compensated. All of those things affect how well people perform. And I know this is a typical solution to a problem that you found in a plant recently, put more people on inspection. But it was really fascinating is actually, if you have too many inspectors, they all abdicate responsibility for detection, and they will actually find fewer objects than if you had fewer people on the line. So psychology of humans is fascinating. It's not just their eyesight that dictates how well they find foreign materials. So if you look about, other automated detection systems, whether it is metal detectors or hyperspectral imaging, those are affected by only the environment and the defect type. Some of those social and psychological aspects and even some of the organizational aspects do not affect automatic detection systems. And that's why I assume many of you are here to listen about what's out there and what technologies you can use. Okay, so the next, most often used technology in a plant is metal detector. And these are fantastic at finding ferrous or iron-based or conductive materials. And they can find very small objects. They're super fast, super easy to clean, easy to install. The technology has been proven for decades. But if you have a product that has high acidity, presence of salt, a lot of water ions and whatnot, metal detectors start not performing the way they should. They can't detect anything that's not conductive, like plastics or rubbers, and have problems with some of the typical metallic materials, for example, stainless steel. You can tune for stainless steel, but then sensitivity to other materials falls. The other thing is they really can't tell you much about where something is. So it triggers an alarm. We found something, but there is no that spatial information about where some foreign material might have. So the next technology that most people use are X-ray detection systems, and these tend to go at various locations of the line. They tend to be placed close to packaging, but oftentimes inspect incoming materials. And again, this technology is extremely well understood, has parallels in medicine. You know, most of us have had some broken bone or potential of a broken bone. So we know that this technology is very good for finding some interesting fractures, dense materials, and whatnot. What's great about X-rays is they penetrate through packaging. So we can have a box, plastic or cardboard, and X-rays see through the packaging. But the problem is that we have issues finding low density objects. And that is really one of the key issues why X-rays are not sufficient in detection of foreign materials in a modern plant. They cannot find things like cardboard, wood, or low density plastics, so conveyor belts, pieces of glove, and so forth. Um, However, embedded metals, there is no better system to find foreign materials than X-rays. And again, as we're progressing down the technological path, presentation of your material is critical. So, for example, the X-ray, water stops X-rays to a certain degree, but thickness of the material is very critical. So, for example, a thick chicken breast will stop more X-rays than a thick chicken breast. And that will affect how well you can detect heel bone, for example, in a thicker breast than in a thinner breast. So again, presentation of material starts becoming critical. You know, I've seen X-ray systems that can detect relatively low density materials. If you have a very uniform thin layer of, let's say, chicken nuggets, it is possible to find some low density materials just on very small differences in pictures. However, if you have overlapping chicken nuggets, it's becoming more and more difficult to detect those low density materials. And this is trying to illustrate a little bit on how X-rays work. So essentially, X-rays are high energy particles that go through an object, and high density molecules absorb the X-rays. And therefore, X-rays don't pass all the way to detector. So you have like a grayscale or just number of X-rays that pass through a material that you're detecting. So really, it's a black and white image. And in this instance, for example, you can see that thicker portion of the breast, of the chicken breast, stops X-rays more than thinner portion, or a portion that's thinner and that has more fat in it. So bone is almost very difficult to see, and you have to start playing some other tricks with X-rays. So this shows a low energy single energy X-ray, and that's why many of you will now be very aware of dual energy X-rays. I believe most systems sold these days in the meat industry are dual energy, and what happens is essentially two types of detectors are used to count the X-rays that pass through something. So high energy and low energy. And you can see that the contrast generated by these two energies is much improved. And when you have this contrast with kind of two grayscale images, you can now compare them, you can divide them, you can start seeing what are the differences. And a lot of the newer X-ray systems do that for you, that math for you. So you're hearing about, you know, material detection X-rays and so forth. Most of them work on the principle of having two energy images, processing them, and trying to find those differences of densities of molecules through which X-rays pass. But again, is this a bone or is it just a thicker piece of chicken is still a problem. So again, even for dual energy X-rays, low density materials are really only possible to be detected when you have a very uniform in texture, uniform in product, and uniform in thickness materials. Okay, but X-rays penetrate through the entire object. So now we're going into systems that are unfortunately not penetrating and are surface only. So a lot of people, kind of go, well, if human eyes can detect foreign materials, why don't we just start implementing cameras? So really, it's something as simple as something similar to your iPhone camera or your phone camera is installed above a conveyor belt. And let's look at images using mathematics and AI and image processing. Can we detect things that look different from the background? And these systems have been around for a while, but we're starting to find that they're not perfect. So, why do we have blues in our plants? Humans can differentiate blue from meat colored objects, and cameras can differentiate blue better from pinks and whatnot. So that's why we have a lot of materials that are specifically colored very differently than the background material. And cameras then can pick those up. The problem is, if something is colored a little bit closer to meat, so like a cardboard or a white conveyor belt or, orange glove, vision systems, just like humans, have harder time finding these. But again, technology that has been around forever, very easy to implement, quite inexpensive. It just finds, for the most part, blue plastics. And this is kind of an illustration of what a typical image would look like. So essentially, it works the same as your eyeball. It collects wavelengths in, detection has a pixel that is sensitive to blue light wavelengths, collects those photons and collects the green photons, collects the red photons, and creates this three-color picture that we are all able to see because our eyes see blue, green, and red photons as well. So not much different than the human eyeball, but we can distinguish, gray from background. But white objects, for example, are a little bit more difficult to find. Okay? Now, we're starting to see something called multispectral or hyperspectral. And what a lot of companies are talking about hyperspectral, what they really mean is that a system sees more than 3 colors. So for example, 6 or 10 colors. And we've seen some entrances of multispectral systems in the market, but the increase of cost and not much differentiation from vision systems, typical vision systems, has really kind of slowed down the adoption of multispectral systems. They can only see small number of wavelengths, and they're not that much different than vision systems. So what does this look like? Well, instead of having the red, green, and blue sensitivity, we now might have sensitivity to 10 colors. And we're collecting pixels that colors at different wavelengths, and then try to see if we can differentiate different materials based on those colors. The step up from a multispectral system is hyperspectral system. And this is what PPO or our company is really good at. What this allows us to do is see continuous wavelengths of light as they interact with the material that we're inspecting. And what that gives us an idea about is different photon wavelengths get absorbed by different atoms and molecules at different rates. So it's almost completely chemistry-based measurement. Now, it is a surface measurement, so again, we can't penetrate too deeply into a product, but we can start looking at chemical signatures as opposed to just colors. So to give you an idea, a white piece of fat and a white piece of rubber to our eyes or camera system can look almost identical. However, because we see this variation of color um, from across a continuum of spectrum, we can actually start seeing chemistry. And this technology has been around now in meat plants for well over 5 years, and we're starting to really show that this technology helps to find foreign materials independent of density. It's and even materials it has never seen before. So, for example, we can tell, did you introduce a new white plastic in your plant? We can now see a signature that this is not meat, but it is some plastic we haven't seen before, and we can talk to you about what is happening and even pinpoint which new machine, for example, is generating these foreign materials. Now, there are some drawbacks to vision systems. And for example, as I mentioned before, these are surface-only measurements. So you have to somehow flip or look from underneath an object to look at all the sides of the product that we're inspecting. The other thing is, just like human eyes and cameras, unfortunately, if something is very thin and transparent, it's more difficult to find. So we're finding perfectly ripped thin films sometimes are difficult to find. Entirely black materials, because they absorb light, are difficult to find. But again, there are some tricks that we can pull like any other technology. We can get some more information than just color or intensity of light, and that gives us an ability to train our system to better detect foreign materials. So what does this look like? As you can see, our system sees continuous wavelengths of light, and these dips, for example, where there is more water, where there is less water, are very, very easy to see, easy to measure, and easy to correlate to a given chemistry. And therefore, we can differentiate something that might look almost identical in vision or multispec. We can differentiate it quite well using hyperspectral imaging. Heather, I'm just going to pause a little bit because I know I threw a lot of information at people. Are there any questions that anybody has?
So one question did come in through the Q&A, so maybe we can address that now because this is a good opportune time. The question was, how successful is this system at detecting clear plastics on beef products?
So we we don't again, it really depends on the type of plastic. We do work in near infrared. Some clear plastics that are clear to our eyes are actually opaque to near infrared wavelengths. If it's a very thin, quite transparent to near infrared wavelengths plastic, we're quite poor. However, what's interesting in plant conditions, it's very rarely do you see a one thin uniform layer of plastic. Something like edges or overlapping plastic or bunched up plastic start looking more and more opaque. So it's not a perfect detection curve. I would say we're looking at a curve that really depends on what type of plastic it is. But for the most part, we do detect some transparent materials. So even clear, transparent bin liners, for example, if they're ripped, they're quite easy to find. If they're perfectly cut and placed exactly on the surface, very difficult to find. Sorry, I don't have a perfect silver bullet answer for you.
I think that's one of those, there's no perfect detection system questions, right? The other question that's come in is, can this be used on ground products?
Absolutely. Actually, To be honest, ground product is one of the best products that we can look at. It's much easier to present to the system in such a way that the large surface area is visible. And just like anything else, imagine looking at uh, mountains versus plains. It's much easier to, from an airplane, for example, to spot houses on a flat surface. So ground product has much less variability than, let's say, cams, where you would be looking at something that's super thick and super thin all in one image. That would create shadows, valleys where foreign materials can hide. If you have ground product, uh, thinly prepared, fairly uniformly spread, we're excellent on finding foreign materials. And our systems are equipped with ability to either jumble or flip product, so we can inspect more than one surface at a time.
And well, it might be worth mentioning as well that we're already scanning, so we're already inspecting ground product in chicken, beef, and pork. So today, multiple systems in multiple plants and multiple formats of ground product as well. So already happening. Happy to show you what's going on if you've got questions later.
I think I have some examples in a moment.
I think you might too. Okay, that's the list of questions, Ola. So
All
back
right,
to the presentation.
all right, off I go. Comparing technologies, we were fortunate enough to work with one of our customers quite recently, where they tested multiple technologies side by side for the same problem, the same materials, the same product. And essentially what happened is they started putting foreign materials, about 15 types of different sizes on the product, and then looked at how many of those materials were found by these three technologies. So hyperspectral, standard vision, and X-rays. They would stop the experiment at the lowest size of the material that the system could find. And there was a requirement that anything about that the materials to be found really had to be in that 10 millimeters or less size. But frankly, they wanted to get to 3 to 2 millimeters. So what they started comparing is what could all these technologies find? And as we know, X-rays were really good at finding metals, some bone. In their case, though, this was pork, and some bone was not possible to be found with X-rays. But they were great with metals and high density plastics. Standard vision systems had some was only able to see high contrast materials, and then hyperspectral was able to detect many of these products. Now, where we failed was actually kind of to that question about transparent films. We were not able to see glass. We were able to see plexiglass, but not glass, which is transparent to all wavelengths of near infrared light. Now, the other aspect of the hyperspectral system is because we see chemistry, we were able to provide other information about the product as well. And this is a little bit more detailed information about what products were we able to detect. And the detections of PPO systems, I believe nothing below 5 millimeters. Everything here is smaller than 5 millimeters. Many of them, some of these like blue acetyl belt, for example, went down as little as 1 millimeter. But different objects are found, or different materials are found at different sizes. So again, I'll be happy to answer any questions you might have towards the end of this presentation. Okay. And here are some examples. So these are zoomed in pictures of actually ground product. And you can see this is a little rubber glove of about 1 millimeter. This object was detected on our system. And again, our system did not over-reject. So we typically aim to reject less than 0.5% of the total volume of product going through our system. And that's by volume or weight. The other example here is, and I can't see it, so if you can see the cotton glove, that's great. But we were able to find this. So cotton glove that's absorbing the fat, the water from the meat. Still, we saw enough of a spectral signature there that we were able to reject it. I don't think any human, any camera, any X-ray system could possibly find something like a cotton glove. And here are examples, we obviously these are placed objects, but something as small as 3 millimeter of cardboard, again, very difficult. This is very zoomed in image, would be very difficult to find by human eye on a moving conveyor belt. And a piece of wood, all these would be found by our system. This is one of our sales engineers, loves this picture. What happened is our system was installed, and in the first few weeks, this little speck of glove was found. Well, nobody, most people couldn't believe that this was possible. And not only did we find this speck of glove, because we knew that a glove was cut somewhere, lo and behold, the production supervisor was able to locate the glove from which this piece came. And this was, again, only possible because we immediately rejected, immediately showed the product, the foreign material, and it was possible for the supervisor to figure out where did this contamination come from. So the good thing is they didn't have to quarantine any of the product. They didn't have to inspect any other bins because they knew exactly that this isn't an entire glove that got chopped up, but a little piece that came through it. So the quick response that our system enabled was very beneficial to this customer. Okay, so I talked a little bit about technologies and showed you examples of what we can do, but let's talk about foreign materials in a plant. And, the Meat Institute recently released a new sanitary design principles manual and has released a foreign materials manual. And they obviously talk to the entire industry and are starting to see that foreign material issue is not just, equipment issue. It is an issue of the entire organization and the entire process of processing meat, whether it's a harvest facility to secondary processing. All of us have an impact on what it means to have foreign materials in our products. So when you're starting to look at how do you solve foreign material problems, that kind of holistic view of the entire process has to be considered. What kind of training do people have and impact? What's the environment? What kind of equipment are you using? Are your suppliers using different methodologies of finding foreign materials, or are they pretty laissez-faire about what's going on in their plants? What kind of raw materials, packaging, chemicals, and all of that, what are you using in your entire process that could create foreign materials? And once you kind of assess that risk, now you can start looking at technologies and other ways of mitigating foreign materials. Many of you start with that mantra of let's make sure that we don't introduce foreign materials in our product first, and then add technology to it. How do you stay clean? How do you make sure that, gloves don't get nicked? Conveyor belts don't get chipped. Do you inspect your equipment and all your protective equipment every day after the end of the shift? That will prevent foreign materials from entering your stream. But again, nothing is perfect. No prevention technology, no prevention method is perfect. So what are the technologies you can look at? Again, metal detection, stainless steel is a little bit difficult to find. Is the product uniform? Does it change its composition dramatically? Do I have to tune my metal detector? X-rays. Are low density materials a problem in your plant? Are you using wooden pallets? Are you using a lot of plastic bins? You know, is your product, incoming product, packaged in cardboard boxes? All of that will impact what kind of materials you can expect in your stream of product. And then, camera-based systems, if most of your materials, you have spiral chillers, for example, and all of them have blue conveyor belts, maybe you can get away with a simple camera system. But do you have embedded foreign materials? Do you have something that are deep embedded plastics or deep embedded metal shavings, for example? Then you might need to look at an X-ray system still. And then hyperspectral systems, just like the question about that we had, also aren't a silver bullet. Some things that look very similar to each other. So, for example, bone and calcified cartilage, or bone with a thin layer of transparent plastic on it, will look almost identical, and our algorithms will not be able to tune that out properly. Okay. Some pieces of cardboard that absorbed a lot of bacon grease, for example. Could you detect them on the background of bacon? Well, is it cardboard or is it bacon grease? What I kind of showed before, that threshold of rejection needs to be tuned to your product. Maybe you're okay with some greasy cardboard going through, or you're going to be rejecting 30% of your production. What's the trade-off that you're willing to do? The other issues here is, shiny metal, shiny water. Do we really need to reject every shiny pixel or every black shadow or black gasket? So again, we tune things around. We try to find different methodologies to help you find these materials that are atypical. And one of the questions, we have a customer right now in chicken in Europe, where they use about 12 different bin liners, depending on where the product is coming from. And some of the bin liners are very thin and transparent and very pale colors. And some are, very thick, dark purple colors. Obviously, the dark purple will be much easier to find than a thin, pink, transparent bin liner. Those discussions are critical when you're purchasing a detection system. What is your specific problem that you're trying to solve? Are there other methods of solving that problem? And then you can talk with us. What can we do? What can we tune? How can we change our approach to maybe find the most problematic material that you have in your plant? The other thing, and yes, I think this is the most salesy slide of this presentation. PPO prides itself on how we support and service our systems. It is not sufficient to buy a piece of equipment, especially when it's high technology. So your X-rays, maybe you can get away without servicing metal detectors for a while. But for your X-rays, vision systems, or hyperspectral systems to do justice to the problem that they're solving, you need good support and service. Your team needs to be well trained and educated about what the systems do and where they could fail, and what to do about those instances where something is not going right. So it's super important to ensure that whoever you're talking to about detection systems, they are willing to work with you and become a partner in foreign material detection throughout your process. Now, this is a little bit, I find this fascinating because everybody in the plant has a slightly different approach of what it means to measure a return on investment of a system for them. So FSQA has very different thought process than engineering or operations. And here are some questions to consider, do foreign materials prevent you from retaining your customers? So for example, we had one instance where somebody was about to lose one of their significant customers because they had major issues with foreign materials. Chargebacks were going through the roof, but the problem was the customer had a very well recognizable brand and they didn't want to have yet another recall due to this customer of ours. By implementing a PPO system, they were able to eliminate hundreds of foreign materials within a day. And therefore, their product quality improved dramatically and they were able to retain a customer. One customer was able to move a product that they were considering for rendering into actually a sellable product because they knew they reduced foreign material presence in that product dramatically. And this was extremely highly processed product. You know, we have examples of customers that save on labor. They don't have the 10 people that were put on a line 3 months ago because there was a foreign material scare from a customer. You know, they can remove inspectors and maybe have 1 or 2 on the line. Reducing food waste. Again, do we discard a combo or half a day of production? Do we ship this to a secondary inspector before it goes to our customer? All those considerations are critical. And then one of the biggest wins we provide to our customers is chargebacks. You know, primary processors, if your product is cleaner going to your customer, they will like working with you and, you know, they will not issue many chargebacks. And that's a significant savings for primary processors. So these are kind of the questions that we tend to ask. And I think, again, as you're thinking about detection methodologies, it's a good idea to ask these questions of your entire team. You know, how many foreign material instances have we had in the last month? Do we think that we found most of the materials or we didn't find most of the materials that were going through the system? You know, some of you have exceptional spot checks and some of you don't. So how do you know what the issue is? How many foreign materials are you actually creating on a daily basis? You obviously are not finding all of them. Are you finding 2% or 80% or 98%? That really impacts what kind of technologies you should be picking. And then, you know, a lot of what we're starting to see, some of our customers are finding that using technology is actually a selling point of their systems. So, you know, we've all heard the high-end QSRs are asking their processors to implement certain safety procedures. What if you're proactive and you implement a safety procedure? So now you're competing with 1 or 2 plants as opposed to with 20. All of those aspects are important to consider as you're looking for detection technologies. So I'm going to stop here. Here's a little list of resources. We will be sending this as a clickable presentation to you. So you can look at these other resources. But I would strongly encourage you to come and visit the PPO website or ask your questions now, and hopefully I can help you out and with whatever problem you have. So Heather, off to you.
Okay, thanks, Ola. One question that has come in is, can you detect Listeria or Salmonella or some of the other microbials that are a problem in plants?
That's a great question. And that detection curve that I was showing you, the smaller something is, the more difficult it is to find. So some systems like ours, we are able to find biofilms. So for example, something is already quite off, but maybe you can't detect it by smell or feel yet. Chances are hyperspectral system can find it. Can we detect one of the 7 organisms that will still infect somebody? Absolutely not. This is still, you know, there is no technology that doesn't take some time, some sort of growth medium and whatnot to find pathogens.
Awesome. Thank you. All right, another question has come in on the multi and hyperspectral imaging equipment. Can you talk about the ease of wet cleaning and sanitation? Are they IP waterproof rated?
Yes. So essentially, most modern equipment, there is no way that it can be designed poorly. Most of us, most of the detection companies will use the standard design processes as outlined for example, in the Meat Institute for Sanitary Design suggestions. And most companies, detection companies worth their salt, work very closely with their customers to make sure that their systems are cleanable, safe, and robust. For example, we have worked with many customers. We have, pre-wash in place ability, conveyor belts that move, sloping surfaces everywhere, bolts that are, always always sloping, and there's no standing water, round, not hollow tubes, things like that. We're really, really paying a lot of attention, not only for sanitation, but also for entrapment of potential pathogens. So again, happy to, we do have multiple videos of sanitation process on our website. And if you have more specific questions, please contact us and we can walk you through how our system helps keeping your plant clean.
One thing that might be worth mentioning is because, as we mentioned earlier, we are in a number of different plant environments already. We have seen some other systems, multi-spec, but also color-based camera, where they need to be sanitized more often. So sanitation between shifts or even during a shift is a requirement in order to keep detecting. With PPO, every plant we're in, doesn't matter what the product is, we are sanitized once a day during the normal sanitation process, and that's it. So very important, I think, to make note of that. Okay, one more question, Ola, and that is, we've talked about X-rays and four materials, but we haven't talked about X-rays and lean point. And what does X-ray do versus, say, a hyperspectral system in lean point measurement?
That's it's quick answer is X-rays to get to lean point use way more math than we do. It is an indirect measurement. So essentially, what I was talking about is X-rays, a single energy will really give us only how many X-rays were stopped on the path between the source and the detector. So not much can be done there. But using dual energy X-rays, you can now kind of do a difference about what molecular weight, essentially, your product is, and then you can kind of calculate the highest density material in there. So protein, right? And then you can calculate fat percentage based on assumption on how much water there should be in protein, and you can calculate fat. So it's a almost a lookup table of what typical meat density is, how much of that is protein, how much is fat, and how much is water. And you kind of lump them, try to separate them through lookup tables. A hyperspectral system, because we see chemical signatures, we actually can directly measure water peak, fat molecules and protein molecules separately and give you each component as a percentage and its direct measurement. Sorry if I got a little bit too much into physics here.
That's allowed. You have a background in it, and it's helpful. Okay, I think that's all the questions. So thank you very much to everybody who joined us today. We really appreciate it. We will follow up via email with the recording and also with the slides, so you'll have them handy. And we look forward to connecting with all of you in the coming weeks, perhaps after the holidays, if not before. Oh, there's one more question. Do you have applications for the cheese industry? Someone got in at the last minute.
You know what? This was one of the earliest areas that we investigated, and we don't have a system in the cheese processing right now. However, we've tested this, and obviously, yes, we can find some foreign materials and composition of cheese and milk products.
Awesome. All right. Thank you all, and enjoy the rest of your day. Take care. Bye for now.